Okay, this is the organic question. Again, we've been given some information and a series of reactions or conditions to try and sort out what the different molecules are. So obviously just your understanding of reactions, etc. is coming into play here. And some additional information down the bottom here. A can exist as enantiomers, which means it must have chiral carbon. And C has a 6-membered ring. Now when we look at C, we've got 6 carbons, so that immediately we should know what C is. Now, a 6-membered ring is just going to have 6 carbons around, well, in a ring. Now obviously you've got to have H's coming off. Now there's 12 H's and an O, and one thing that should be apparent from looking at this reaction with sulfuric acid, that's dilute, and we've got C10 H18O3, and we get this split into two, is that this is hydrolysis of an ester. So with only one only one O on this side, that would mean that there's a good chance that this is going to be a alcohol on here. So that would give us C pretty much straight away, just giving us that piece of information down here about the ring. And then we're going to have to figure out what's in this one, which has got dilute sulfuric acid. And, when it gets reacted with dilute sulfuric acid, we get C4H8O3. And the fact that we're considering this is probably an ester, that's probably a carboxylic acid. And that would also mean that there's a possibility, if there's another O present, that we're dealing with a OH coming off somewhere on that one as well. So we just need to work through this logically. Now obviously it's helpful to get a head start on what A and B look like, and if we consider that B has got 4 carbons in it, all I've done for A here really is just kind of draw it out. And this obviously isn't A, this is just a guess at what A might be, and I'm going to try and do some eliminations. Now I've put O ring here just to indicate that 6 carbon ring, which we've already deduced what it is. So we're not terribly interested in it, we're interested in what's on the left hand side, on this side. Now we're told that it must be an enantiomer, so straight away we should be thinking about there's probably a methyl group coming off there somewhere. There's also an OH group here, an alcohol, because there's 3 oxygens and I've only got 2 in here at the moment. So that's going to come off somewhere here. And so at the moment we're just trying to deduce what the actual chain looks like. Now if I was to put the CH3 group here, obviously that would just be the same as this one at the top. If I leave it where it is, or put it along, then it makes it much more difficult to get an enantiomer. In fact, we probably can't do it. In fact, we can't do it. So this one here must be the basic kind of structure of the chain. We must have a methyl group of it, of that carbon there, the second carbon in. Now, an OH group, well, where's that going to go? Now, if we put a OH group here, for instance, the problem with that now, we've got a CH3 group there and a CH3 group there, and this does not make this an enantiomer. So for A it won't, for A it would not make it an enantiomer. So we have to consider that the OH is going to go on that one. So that would give us what A and B are going to look like. Okay, now in drawing out A, that ring's a bit of a pain to draw out, but there you go. Just take care with the join here. And here's B. So from B, we should be able to go on from this a little bit easier. So, and that's what we'll do. Okay, and we're told that with B we have conc sulfuric acid, and you should realize it's going to form a double bond in here. It's only got one place to go, so obviously we're going to get a double bond here. We've still got the methyl group coming off, and it's just really a matter of redrawing everything else, taking care with a number of H's. And so that's obviously going to be D. So we've got 4 carbons, 1, 2, 3, 4, 5, 6 H's and 2 O's. Now D to E, now that's permanganate. We typically think of it as an oxidizing agent, and if you had an alcohol you'd be thinking maybe about it oxidizing that, if it was primary secondary that is. But at this stage we've got a double bond, and you should remember that that's going to form a diol to form across that double bond. So what we'll do here is, and that's just a matter of again of drawing that out with an OH here, double bond of course disappears, and oops, we've still got the methyl group there, so I'm going to still show that obviously, and that structure is going to be E. Now E to F, I've got dichromate, and just a point to remember, whenever we're talking about using dichromate or permanganate, always remember to mention the conditions such that it's acidified, which is what the H plus stands for. This is obviously a primary alcohol. Here though, because this is a carbon here, that's a carbon here, that's a tertiary alcohol. Easy mistake to make to just think of it as being a secondary one, so that when we undergo oxidation here we're going to get probably a carboxylic acid, but again you should check to make sure that you have the right number of carbons, etc., hydrogens and oxygens, just in case it's formed an aldehyde, which is a possibility. And if we go through and count 3, 4, 5, 6, 1, 2, 3, 4, 5 oxygens, that's the correct structure for F. And now we've just got one left, and that's going to be G. Now, with concentrated sulfuric acid being added, one of the things you should be thinking about is maybe that can make an ester if there's an alcohol and an acid, but also maybe it can make a double bond. Now it'd be easy to look at this and think it can't make a double bond because you're focused on these carbons here, but this carbon here has some H's attached to it, so we will in fact get a double bond forming there, and that's going to be G. And that should be the final product, and that's that question complete.